In the last lecture, we had discussed super dense coding. We had pointed out that the coding or the dense coding or super dense coding arose out of the desire by Alice of sending some classical information by sending a lesser number of quantum bits to Bob. In this lecture and the next one, what we intend to do is to talk about the real systems which one actually considers. See, when we stated the laws of quantum mechanics or the postulates of quantum mechanics, it was assumed that we are talking about a closed system, a system which is there by itself, does not interact with outside systems. In other words, our definition of the system was a self-contained system. Now, generally, what we consider are or study are much larger systems. Now, what happens when we study much larger systems are the following. One, our first postulate was that the states are represented by rays in a Hilbert space. Now, that postulate may not hold good. And as I go along, I will sort of explain by giving examples of why I am making that statement. The second thing that we talked about so far was that we talk about measurements in a computational basis or even other basis, but basically the measurements which are orthogonal projections onto your basis states. Now, that may not necessarily be applicable. The third thing which we assumed is that the evolution is unitary. Now, this postulate also may break down when we do not consider closed systems or what we will be talking as pure system. Now, let's see this with an example. So, this is what happens. Now, just to give you an idea is the following. This open systems is essentially a collection of systems. So, let's just, for giving you a trivial idea, consider a two-dimensional system whose basis states are x, y. It could have been 0, 1, it doesn't matter. And supposing I have an ensemble, I have a collection of states, but the states are not of one type. So, I have a state or type of state which have their state vector psi as alpha times x plus beta times y. You could have taken them alpha times 0 plus beta times 1, doesn't matter. You have another type of state there which is in the same basis written as gamma times x plus delta times y. Supposing I had n number of states in the system, then n times p is the probability, n times p is the number of states in the first category, and n times 1 minus p is the number of states of the second category. Now, the question that we ask now is that supposing we measure this system in a computational basis, 0 and 1 or x and y in this case, what is the result that we would get? So, the point here to note is the following, that what is meant by a measurement in this case. Now, when I make a measurement, what I have to do is to pick up one of the states belonging to this ensemble. Now, when I pick it up, whether it belongs to the state psi or it has a state phi, that is determined by the probability with which my mixture or the collection was prepared. But that was a classical probability. So, I said small p is the probability that in my collection the state that appears is psi, and 1 minus p is the probability that the state that appears is phi. So, when I make a measurement, I need two things. I pick up a state and I know with probability p it will be psi and with probability 1 minus p it will be phi. Having done that, I would make a measurement of that picked up state in the computational basis. So what would I get? So let us come back here. So let us suppose I have a state psi, and that we have said is alpha x plus beta y, and it could have been a state phi which is gamma x plus delta y. Now when I picked up at random, if I happen to have got this state psi, then my probability that my state collapses to, let us say, x. Now this is given by p times alpha square. Now this is provided I have picked up the state psi. But if I happen to have picked up the state phi, which is done with a probability 1 minus p, and the probability of getting state x here is gamma square. So this is the product of two types of probability. This is a classical probability p and 1 minus p, and this is the Born probability. And this p and 1 minus p, they are classical probability. Obviously, the probability that it collapses to a state y is given by p times beta square plus 1 minus p times delta square. So when you consider a general system which does not contain only one type of states, this is the extra considerations that comes in. Consider, on the other hand, a composite system. Now supposing I have a composite system, and let us suppose the composite system I will call as A cross B, and the corresponding Hilbert space is HA cross HB. Now suppose I have psi AB as a state in this Hilbert space. Now if it so happens that psi AB is factorizable, remember we are using the word entanglement, we are saying if the states are not entangled, then I can write psi AB as product of psi A with psi B. Now when such a thing happens, if I consider an operator, supposing O is an operator, OA is an operator, which measures some property of system A. Then what I am trying to do is psi AB O A psi AB, psi AB. Now since this acts only on A and this is factorizable, I can write this OA as product of OA direct product with IB, where I is an identity operator on B, and then this will give me psi A OA psi A multiplied by psi B IB psi B, but that is equal to 1 by normalization of the psi B's. So, this is what I would get. So, in this case, the system behaves like a pure state. So, there is no entanglement. So, no entanglement. The composite system behaves like a pure state. Now, notice, if the system does not allow such factorization, the usual nomenclature uses, supposing A is my system of interest and B is an environment. By the word environment we mean any system with which the system A interacts. It need not be a big system, it can be as small as the system A itself. So, if the interaction is such that the wave function does not factorize, then the above argument does not work, and we need to extract information about properties of system A by a different idea. Such systems are known as mixed system, mixed state. Now, what we are going to do in this lecture and the next is to talk about the postulates of quantum mechanics as they need to be modified for such mixed system. Continuing with our example, let us consider a very trivial case of a composite system which is entangled. So, what I have done is to take psi AB is equal to, suppose I write it as some constant times 0 A, 0 B. So, I am taking a single qubit state to be both A and B, and so the basis is 0 and 1 in both, but this is a composite system. So, I write this as this plus, let us say 1A, 1B. This is obviously not factorizable. So, the question is this, that how do I calculate? Supposing I have an operator in the state space of A and B is an identity. Now, this is the operator which I am interested in calculating the expectation value. So, how does one, what is, in other words, I am interested in finding out what is psi AB, MA cross IB psi AB. So, let us do a bit of an algebra with this same example and look at it the following way. So, here I have written this psi AB like this, and we are going to consider what is the expectation value of this operator. I will do a bit of a formal arithmetic here. So, we have psi AB MA cross IB psi AB. So, let us expand this out. So, we have said already this is A00 plus B11. So, this is the bra. So, therefore, I get a star 0 A 0 B plus B star 1 A 1 B. Then I have my operator sandwiched between bra and ket, and then I have got A, 0 A, 0 B plus B, 0 1 A, 1 B. I can just multiply it through and get 4 terms there. Let me write down the non-vanishing terms first. So I have got A star into A, which is modulus of A square. I have got OA, 0A, MA, 0B, now if you look at it, I have an IB there. So I have got 0B, IB, 0B. So let us write it for formality. 0B, IB, 0B. This should be 0A plus B square, similar term, 1A, MA, 1A multiplied with 1B, IB, 1B. There are 2 more terms. So notice that these terms are 1 because IB does not do anything, just keeps OB, and this is normalized, and this term is also 1. So what I get here is, I will come back to the 2 terms which I have dropped, 0A, MA, 0A plus B square, 1A, MA, 1A. Now what about the terms I have dropped? The terms that I have dropped are the cross terms, terms dropped. So the cross terms, for example, are A star B, 0A, MA, 1B, 1A multiplied by 0B, this is one of the terms, IB, 1B. This is clearly 0 because IB acting on 1B does nothing, and then by orthogonality this is 0. The other cross term also becomes 0. So this is the result I have got. So what is this thing compactly? So this is nothing but A square times the diagonal matrix element of MA plus B square times the diagonal matrix element of MA in state 1. So if I define rho A, you can look at the slide which is also there. So I define rho A as A square, 0A, 0A plus B square times 1A, 1A. This is an operator. Remember that a ket followed by a bra is an operator. This is an operator. So if I define this way, then what I have got here is to write this expectation value as trace. Trace is nothing but the sum of the diagonal elements. So trace of rho A with MA. With this definition, this is what it works out. You can simply plug in this rho A into my previous expression and get this. So this operator that I have defined here, this is called the density operator. This rho A, this is my density operator for the subsystem A, also known as density matrix. These are interchangeably used. We have already pointed out several times that any operator can be expressed in a matrix representation. So, these are known as the density operator. Now, to look at what is the difference between the two, consider the following things. Let me first give you an example. So, of a pure state. A pure state is a coherent superposition of the basis states, for example. So, let me take psi to be given by 1 over square root of 2, 0 plus 1. This is what we have been talking about several times. Now, supposing I take this state and calculate what is the expectation value of, for instance, sigma x operator. Now, you can immediately do this because this is 1 over 2, because a bra and a cat each one will have a root 2. So, I have this, that I have 0 plus 1 operator sigma x acting on the state 0 plus 1. We know that sigma x changes a 0 to 1 and 1 to 0. So, therefore, this becomes 1 and this becomes 0. Just multiply them. This term, this into this becomes 0, this into this is 1, this into this is 1. So, that is 1 plus 1 is 2, by 2 that is equal to 1. Now, however, supposing instead of this coherent superposition, I had a equal superposition, equal mixture if you like, of state 0 and 1. Now, what is the difference? The difference is that this is a pure state, coherent superposition. Here, what we have to do is to look at it. I have a collection in which I have states 0 and state 1 in equal mixture. So, when I calculate the expectation value, I pick up one of them, and that will be of course picked up with some probability. In this particular case, it will be probability of half. So, I will calculate the sigma x expectation value this way. I have a probability half of picking up the state 0. So, it is half of 0 sigma x 0 and an equal probability of picking up a state 1. And since sigma x converts a 0 to 1 and this is orthogonal, so I get 0 plus 0 equal to 0. So, this is the difference there, that this is a coherent superposition, this is an equal superposition of the states. Now, so let us look at how does it work. Now, in this particular case, if you are looking at the density matrix, so look at the density matrix for the equal superposition case. For the equal superposition case, I have got 1 over 2, that was the probability, and I have 0 0 plus 1 1. So, this is, now since my basis state only has 2 elements, this by completeness theorem is 1. So, I have got this is actually it should be I by 2 because completeness theorem gives me this as an identity operator. So, this I should write it as I by 2. I will show in the next lecture that whatever result we proved just now for sigma x, that if I have an observable A and a corresponding operator A, then expectation value of A turns out to be trace of rho times A. We will go through in our next lecture the properties of the density matrix and its importance in discussing systems which are composite systems or open systems.